Good afternoon, class. So remember, we're still doing kinematics problems. So remember, first thing, read the whole problem. The whole one. Not half of it, not parts of it, the whole problem. 2, draw a picture. So make those abstract words come to life in an actual picture that you label. So also label what's happening. 3, write down numbers and variables. Variables you pull from your problem. 4, based on these variables, pick an equation. And 5, solve using that equation. Alright, so your homework was page 22. This is page 22. Problems 1 and 2. I will be going over them with you, but make sure you attempt them by yourself. At least try to get up to step 3 as far as pulling out variables. Something you will have to know, however, is remember that acceleration from gravity on Earth, it's only on Earth, is equal to 9.81 meters per second squared. Although you can just do 9.8. 9.8 will work. Remember, you have to pick a direction to be positive. You have to pick a direction to be negative. So if you say, for example, that down is one way, up is another, I normally say up is positive and down is negative because that makes sense to me, but you can do it any way you want. It's arbitrary. You could say this is positive. Just stay consistent. Alright, so go ahead, try these, and then we'll work on them together. Alright, so number 1, how long does it take a basketball to drop 145 meters from rest? What velocity does it attain? So, I've got a couple things I underlined and I read the problem. That's 1. 2, draw yourself a picture. Okay, so we have basketball up here. Here's the ground. It's going to drop a total of 145 meters. And it right here is at rest. So it's dropping from rest. So maybe someone was holding it. Person who's very tiny who's holding it jumps really high and then drops it from right here. So right here it's going 0 meters per second. That's what at rest means. Remember, that means it's not moving. So it starts here and then drops directly. Now, since it was dropped, we can know, oh, the acceleration from this is 9.8 meters per second squared. It doesn't have to be negative, but for me, I'm going to say down is negative, up is positive. Since down is negative, acceleration for me will be negative. And then we got to start doing some other things. So it went a total of 145 meters, so I can say it started at 105, and I'm going to call the ground 0. So now I can start listing out my variables. I know what A is. I know what X initial, where it started really high up, so it started at 145 meters. It ended at 0 meters, it hit the ground. We know that its initial velocity was 0 meters per second. We don't know how fast it's going at the end, and we don't know how long it took. So what can we do? So for each one of these, for finding velocity, the final, and time, you will need to have a brand new equation. So looking at, let's do how long does it take. Let's do time. So for now, we don't care about this. So we have acceleration, initial position, final position, initial time, or initial velocity, and time. Hopefully, that's led you to this equation. x equals x naught, which we know both of those, plus velocity initial, which we know to be 0, plus 1/2 a t squared. The only one of these we don't know is t. So let's simplify. I'm going to erase our beautiful picture to give us some room. For you, that means write it further down on your paper. So we have this formula, but we can know right off the get-go, we don't care about the velocity term. X is equal to x naught. We don't care about velocity because it's 0, so it's just 1/2 a t squared. Now again, I would argue that you should probably solve this for a first. If you don't like that, you want to plug in your numbers now, you can do so. I'm going to solve it. So first, we want to figure out what t is, so get everything around t away. I'm going to make t a different color here. So subtract your x out, so you're going to have x minus x naught equals 1/2 a t squared. Then we need to essentially divide these out, or I like to think as multiplying. So we have a 1/2. That means essentially you're going to have to multiply by 2 and then divide by a. So this will cross out and this will cross out. Do it to the other side. You're going to get x minus x naught, do put it in parentheses, over times 2 over a. And this will give you t squared. Finally, you have to square it. Once you square it, that gets rid of your square rooting, gets rid of your square. And so now you essentially have a plug and chug equation. You know all those things. So now you just plug it in. So you got 2. This is 0 minus 145. So you're going to get negative 145 meters over a, which is negative 9.8 meters per second squared, which is equal to 2 times negative 145 meters over negative 9.8 meters per second squared. You can pretty much just plug that into your calculator. You'll notice your meters are going to cross out here. And don't forget, you do have to square root all this because you have this squared seconds here, so you know that you must still square root it and plug it all into your calculator. 2 times 145 gives you 290, negative 290 over 9.8. Do the math. Gives you, remember the negatives cancel out, gives you 29.5 or 29.6, excuse my rounding, and then you must take the square root of that. And this should give you, if you square root it, 5.44 seconds. If your rounding's a little off, that's fine. If you got in the realm of 5 seconds, you're doing good. Alright, now I'm going to erase all this because now we got to figure out what is the final velocity. Alright, so we are now trying to find the final velocity. We now know the time, but we really don't need it because if you look, you can find out, there is an equation that doesn't use time. And it is final velocity squared equal to v naught squared plus 2a x minus x naught. Now this is really helpful, right? It's pretty much done exactly the way we need it, so we can just kind of start to solve from here. We can just start plugging in. This term goes to 0 because it's still 0. So we're going to get 2a but we know A to B. So we know that A is going to be negative 9.8, so you can just plug in A now. And apparently my program's having issues, so hopefully give it a second. So now it looks like it's in a loop, so let's just kill some things here because it's obviously having some issues. So now we just have to plug in numbers. Sorry about any issues there for the last couple minutes. So we have 2, negative 9.8 meters per second squared. Then you're going to get your meters, which is 0 minus 145 meters. So you're going to get negative 145 meters. 2 times negative 9.8 gives you a negative 19.6. So all equal to b squared. So then multiply those two together, and you're going to get a really large number, which is positive, which makes sense, because now we have to take the square root of it. Take the square root of both sides, and you will get 53 meters per second. If you're confused about the units, our units here, let me do it in a different color. Our units here were meters per second squared. Then you're timesing it by another meter, so you're going to get meters squared over seconds squared is in here. And then you're taking the square root of both of them, which kills all your squares. So now you just get meters over seconds. So that was all number 1. Whew. Good job. On to number 2. And always when you're doing this, think, does that make sense? Think, it fell from 145 meters about over one football field, and we're assuming it doesn't ever experience air resistance here, which means it's going to be going pretty dang fast at the end. Alright, so now we have problem 2. Read it. An astronaut dropped a rock. So an astronaut dropped a rock from some unknown height on the moon where the acceleration or gravity, that's going to be an important number, is 1.6 meters per second squared. The rock took 10 seconds to reach the surface. From what height was the rock dropped? Alright, so let's draw a picture. So we got some astronaut. He's puffy because he's suit. He's on the moon. He has this rock. Maybe he's on a cliff, I don't know, and it's going to fall down, but not quite as fast. It's going to be at acceleration is going to be, and again, I'm going to call this negative and up here positive, so it's going to be negative 1.6 meters per second squared. We know that the time took 10 seconds, and given all of this, I want to know what is its position, or essentially its change in position. You know, how high was this rock? So I'm going to call where the rock landed 0, which will give us, I always like to make the ground 0. It's in my head that makes more sense. So we actually do know its final position to be 0, but we do not know where it started. Where was it dropped from? Alright, and then looking at this, you know, there's a couple of things we could use, but we're missing some variables. The main one we're missing is, how fast is it going? Well, we don't know how fast it's going at the bottom, but if it's in an astronaut's hand and he just drops it, how fast was it before it started accelerating towards the ground? Hopefully you can understand that initially it was only going 0 meters per second because he was holding it. Therefore, it was not going anywhere. Alright, given all these variables, you can see there's really only one equation that contains all of them, and that's our main equation, is x equals x naught plus v naught times t plus 1/2 at squared. Now again, our initial velocity is 0, so we don't care about this term. And you can either solve for x naught, or you can just plug in numbers. I'm going to solve for x naught. So after we get rid of the term, we have x naught plus, these positives still stay, 1/2 at squared. So don't be so confused by this jumble of things here. We don't care that they're all together. We only care that they're currently being added to this x naught. So we only have to subtract it. That's all we need to do. So the whole thing is x naught's going to be all by itself here. It's going to be equal to x minus 1/2 at squared. Now we get to just plug in some numbers. So x naught, we have no idea, so this stays x naught. Oh, our x is 0 anyway. We don't care. So now we're going to have a negative 1/2. Our acceleration is negative 1.6 meters per second. And the time is 10 seconds, and it is squared. So if you square a 10, you're going to get 100 seconds. I'm going to leave this negative 1/2 times the 1.6 meters per second. So if you remember, if you square this 100, you're also squaring your seconds. Oh, and look, you have seconds squared down here and seconds squared up here. These are going to cancel, which leaves you with just meters, which, ta-da, that's what you cared about anyway. So now we have 100 times negative 1.6 times 1/2. Throw that. Stick it all in your calculator, and if you multiply them all together, you get a nice clean 80 meters. Alright, hopefully this was helpful. Sorry it ran a little long because of those issues I was having throughout the video, and I will see you tomorrow.